However, things become little more complicated and challenging for certain configurations where this sort of reduction in parallel and series arrangements is not possible. So one classical example is this bridge arrangement. So we have a key element E5. So there is no way that this can be reduced to an arrangement as we looked at in the previous slide. 5, just to be sure, is bidirectional. We are going to next look at an example where 5 is actually unidirectional. So how do we solve this? If you want to work through this, please pause the video. Otherwise, let me present the solution. Again, let's note that all the 5 elements are mutually independent. So the way to proceed would be to split this bridge system into 2 simpler systems. So one in which the fifth element, the key element, is working for sure, and the other case where the fifth element has failed for sure. So this gives us the 2 simpler systems that you see on your screen on the left, where because E5 is working for sure, that has been replaced by just a simple link, and on the right, E5 has failed for sure, so that has been eliminated completely. So now we have on the left, we have a simple parallel arrangement in series, 2 parallel subsystems in series, and on the right we have 2 series systems in parallel. So we know how to solve this now. So we use the theorem of total probability. The system reliability is the system reliability given that element 5 is okay times the probability of element 5 is okay, plus the same system but given element 5 has failed times the probability of its failure. And now we can proceed as we have done in the past. So on the first line you see the left configuration which is multiplied by the reliability of 5, and on the bottom line you see the right configuration which is multiplied by the failure probability of 5. Things become even more interesting if we consider the key element 5 to be unidirectional. So we have to modify our approach a little bit since the previous solution to account for the fact that 5 is unidirectional. So we won't condition on 5 anymore, but we'll take one of the others. Say let's take 4. So now we take on the left, as you see, the conditioning event that 4 is for sure working, and on the right 4 has for sure failed. So that's our partition, and our system reliability can be expressed in terms of the equation that you see on the left. So if we just inspect the figure on the right, when 4 has failed, it's a very simple configuration now, because whether E2 is working or not, it has no contribution because it can't reach the N terminal. Likewise, whether E5 is working or not, it makes no difference because there's no way to reach the N terminal. So in effect, it's a series system involving elements 1 and 3. So we'll keep that in mind. The one on the left, where 4 is working, when it's conditioned that element 4 is working, it still needs a little bit of simplification. We won't be able to proceed just with this, but we are going to make one more partition, and that would be on element 3. So on the left we have element 3 working, and on the right we have element 3 has failed for sure. So in terms of writing the first term in the first equation, system survival given E4, we now condition that further on E3. So you see the second equation where we have S given E4, E3 and S given E4 and E3 bar. So it's now straightforward to solve both of the configurations on the bottom pane, and the answer would be for when R3 is working, it's simply an arrangement of E1 and E2. It's a parallel arrangement of E1 and E2. Whether E5 works or not, it makes no difference. So that's the first line on the bottom block. The second line is when E3 has failed, and that is actually that takes into account element 5's reliability, and that's what you see on the second line. And the third line is basically what we looked in the beginning, is when element 4 has failed. So the combined system reliability is computed in this manner.